We'll now take a look at how the operating system handles system security and protection. In addition to being a receptionist, the operating system also has the responsibilities of a security guard, controlling access to the computer and its resources. So it must prevent unauthorized users from accessing the system, and it must also prevent authorized users from doing unauthorized things. So, at a minimum, the operating system must not allow people to access the computer if they haven't been granted permission. Now, in the old days, we're talking back in the 1950s and 60s, security was more physical, having walls and locked doors around the computer and having security guards at them to prevent unauthorized access. Now, this has changed over the years with the inclusion of networks, so it became a lot easier, I should say, to access these machines, even if you have walls and doors and guards. Now, in most operating systems, access control means requiring a user to enter a legal username and password before any other requests are accepted. So if an incorrect username or password is entered, the operating system does not allow access to the computer. But it's also the responsibility of the operating system to safeguard the password file that stores all the valid user name and password combinations. So it needs to prevent this file from being accessed by any unauthorized users, because that would compromise the security of the system. If someone got a hold of the password file, then they would know the usernames and passwords of every single user. Now, there are some exceptions to this. You can have what are called privileged users or super users who pretty much have access to everything in the system. You can also include encryption on the password file, which would encode the file to make it more difficult to read. So there are a couple tricks here that can be done, but the whole point here is that we need to be able to protect the system from people who should not be able to get into the system, and we should also be able to protect the system from authorized people from doing things that they shouldn't be doing. So as we mentioned, even when a valid user gains access to the system, there are things they should not be allowed to do. The most obvious is that they should be able to access only their own personal information. They shouldn't be able to look at the files or records of other users. So, for example, let's say the operating system gets a request such as opening a file. So we open a file and allow this user to access it. So the system must first determine who is the owner of the file. And the owner is normally the person who created the file. Now, if the person that's accessing the file is not the owner, it usually rejects that request. However, most operating systems allow the owner of a file to provide a list of additional authorized users or a general class of authorized users, such as all the students or all the faculty. And like the password file, these authorization lists are highly sensitive files, and the operating systems will store them in an encrypted format to make sure that no one can just get a hold of it and see the permissions right away. So most operating systems not only determine whether you are allowed to access a file, but they'll also check what operations you are permitted to perform on that file. So we can take a look at just a couple of examples here. So you may be able to read a file but not make any changes to it. You may be able to append new information to the end of the file but not change existing information. You may be allowed to change existing information in the file, or you may even be allowed to delete the file from the system. We'll now discuss how the operating system efficiently allocates resources. If you recall a while back, we talked about the differences in speeds between a processor and an I/O unit. A hardware device called an I/O controller would free the processor to do useful work while the I/O operation is being completed. So what does the processor do with all this free time? We freed it up, so what does it do? So what ensures that this resource is being used efficiently? So again, it's the operating system's responsibility to see that the resources of a computer system are used efficiently as well as correctly. So to ensure that the processor does not just sit idle and twiddle its thumbs, if it had thumbs, so to make sure that it's doing something if there is useful work to do, the operating system will keep a queue. which is a waiting line of programs that are ready to run. So whenever the processor is idle, the operating system will pick one of these jobs and assigns that job to the processor. And this just guarantees that the processor always has something to do. We have to make sure the processor keeps doing something, that it's not bored. Although it technically doesn't get bored, it just gets idle. But we always want to make sure that the processor is doing something. To see how this algorithm might work, or working with the queue works, let's define the following three classes of programs. So we have running. In here, we're saying that the one program is currently executing on the processor. And we're just going to assume that there's only a single processor on the computer. Another class is ready. Here we're saying that programs are loaded into memory and they're ready to run, but they're not yet executing. They're in the queue and they're ready to go, but they're not actually running. And then we have waiting, which just means that we have programs that cannot run because they're waiting for some type of I/O operation, or maybe even some other time-consuming event to finish. So let's take a look at an example of a couple programs and kind of see how these lists might look at some instant in time. So here we have 4 different programs, which we're calling A, B, C, and D. And these programs are in memory. Program A is executing on the processor, and programs B, C, and D are ready to run and are in the line waiting to run. So remember that only one program can run at a time. So that means A right now gets some time with the processor to run. Now let's suppose that program A is performing some I/O operation. Maybe it's reading some sector on the disk or doing something else. And what this means is while A is waiting for this I/O operation, the processor really isn't doing anything. It has nothing to do. So the system efficiency just plummets. To solve this problem, the operating system can do some shuffling. So what we see here is that it can move program A to the waiting list because it must wait for its I/O operation before it can continue. So then it can select one of the ready programs. So we'll just say B here, and we'll assign B to the processor. So then we start running B. So now we see here that we have B that's currently running, C and D are ready, and A is waiting. So what this does is it lets the processor work on a program while waiting for A to finish up. So instead of just sitting idle while A is waiting for some I/O, the processor will work on B and actually get something done. So I mean, this is equivalent to working on another project while waiting for someone else to maybe get a document instead of waiting and just doing nothing. Now, at some point, the I/O operation that A started will finish, and then the I/O completed interrupt signal will be generated. So this means that A will now be ready to run, but the problem is A can't immediately run because B is currently running. We can't just say that, okay, B, you get out, and then A goes back in. Now, there are some exceptions to this in operating systems, and we won't get to that right now. But the whole point here is A now has to wait for B to finish before it can get back to the processor. So what we do is we place A back into the ready queue, or the ready list, to say that whenever the processor is free, then it can pick one of the programs in here. And it's actually quite common that we do this. So, I mean, here what we're going to have is that programs are always going to cycle from running to waiting to ready and then back to running. So B may end up getting an I/O operation, so it gets moved to the waiting list, and then the processor will pick C, D, or A and put it into the running list, and then B would finish up and move to the ready. So this is actually very common for a program to stop and restart before finishing. It's actually very rare for a program to go from start to finish without any interruptions.